actual functionality of the hash functions. Okay, so in this hash function, if you see the design principle of hash function before discussing that, as we saw that the hash functions have many practical applications that the range from the simple file integrity check to uh, your the authentication part of that, and they are basically used the hash tables to distribute the hash table among the users, and this technology is basically used in blockchain technology or blockchain to protect the data or to maintain the integrity of that. So the hash functions play a very vital role in this blockchain technology. So especially we know that the proof of work, whether the any modifications that happens in the blocks, whether they are done by the authorized users or not. So this proof of work functions uses this hash, 256 or secure hash function of your 256. So it says that it takes the output of this secure hash function is 256 bits in size. 256 bits in size. So this the design of this secure hash algorithm, this the design principle. So we will discuss this by introducing this secure hash function of your 256, and sometimes the SHA-3 is used, but for our Bitcoin mining purpose we use the 256, and we also call this as your SHA-2 family group of your hash functions, and which is originally developed by the National Security Agency of United States for making the messages as secure as possible in the network. So, what is the importance of the design principle of this SHA-256 means? It takes the any message as an input. So let me just design this. There is a hash function we call SHA-256. It takes an input and gives an output. So what is the input? The SHA-256, it takes the input size of maximum 2 to the power of 64 bits size of message. Okay, so this much length of message that it will take as an input. Okay, so that means it starts from zero, the one character or one character size of your message to 2 to the power of 64 bit message size as an input, and it gives the a fixed length of your digest, that is 256 bit size of your digest will be given as an output. Okay, and in this the messages which it is taking as an input, that message is divided into blocks. It is a message with size of that depends 2 to the power of 64 in max. So that entire message, the input message, will be divided into the blocks. The block 1, your block 2, up to your block of your suppose the 2 to the power of 64 block it is. So entire message is divided into blocks first. So what is the size of this block? The size of every block in this message is 512 bit in size, every block size. This algorithm takes. the entire message divided into blocks. Each block size is 512 bits. And every block is further divided into this small piece of word we call this is one block. That block is divided into words. Word 1, your word 2, and so up to your word. 15 words will be there. So what is the size of this word means? The size of this word is your 32 bit in size. 32 bits in size. Okay. So this is the basic, what you call the prerequisite for configuring or designing this SHA algorithm. Okay. So what is there? There is a hash function. We call this as the compression function also, hash function, secure hash function. We call it as our compression function also. So this compression function takes the input message as the message with any length of message as an input and gives the fixed size output, that is 256 in bit. So for that, to do the compression for this particular message, the pre-processing is required. For that pre-processing, what is the basic information means? It takes the message size maximum 2 to the power of 64 bits. And that message is divided into blocks. So number of blocks depends on the size of your message. 1. So what is the size of each block means 512 bits. And further, each block is divided into words. The size of words is 32 in bits. Okay, because it follows the secure hash function follows the without key it is doing the compression, so it follows the ciphertext, the encryption method. The ciphertext, it follows the number of rounds will happens on the block ciphers. So for that, the entire message divided into blocks, then blocks divided into the words. The word size is 32 bit, and finally it gives a fixed length of your 256 bits in length. 256 bit in length part. So this further, the compression function which we are using here, the SHA-256, the compression function, this has the this function process each block. This SHA function process each block separately in a sequence manner. Like block 1 will be processed first, then block 2 will be processed, then block 3, and so and so. It processes the last block in a sequence. So to do this, I'm not going in detail about the compression functions, how we do. This is related to your block cipher function, which you already, I think, find out in the principles of cybersecurity work. So this message will be processed. Every block will be processed and give this 256 bits. For every block size of your 512 bits, that will be taken as an input, and the internal value, that is the 256, will be considered by this compression function to convert these blocks into the fixed size digesters. So there are two main components that this function is used. One is the compression function, another one is the message schedule function. So before doing that, you do some pre-processing part. In the pre-processing part, as we taken into the consideration that these blocks will be size of 512, but there is a possibility that we talk about only one block. In every block, there is a possibility that there may be less than 512 bits in this block. So then what will be happen? So this, the compression function takes every block size is 512 bits. But instead of 512 bits, If a user gives 1 bit or 2 bit or 3 bit, then what will be done? How this function will be works? Any guesses?
Padding.
Padding, yeah. So in this compression function, the pre-processing is required, like padding the bits, so that every block size will be fixed to 512 bits. So that after that, doing the computational operations or mathematical computations will be easy. So in the pre-processing, the first part is it does the pre-processing one. So we call that in the pre-processing one, what it do, padding the message, which is used to make the length of the block size of your 512 bits. So if it is smaller than the required block size of 512 bits, then parsing the you can add the some of the padding bits. So in which fashion you are going to adding means, if it is less than 512 bits, if you consider any message M and the length of the message is L, and if you do the modular operation of the length of the message with the block size, if it is not equal to 0, means it is the number of bits in that block is less. So you need to add those many number of bits to your block. So how you are going to add? You need to differentiate the original message as well as your padding bits. So to do that, at the end of the message, there is one bit which will be added 1, and after adding 1, the remaining bits will be added in terms of 0 bits. So there will be k 0 bits will be added to your message after entering the 1. So where this k is the smallest non-negative solution to this equation, that we add the original length of the message is L, then if that message is less than your 512 bits, then we are going to padding some extra bits, k0 bits, after adding 1 bit into the original message. So that will approximately 448 bits. If you do the modular operation of that with your 512 bits, then it will give the exact how many bits will be required to add in that one. A bit. So after getting the full length of your block, after doing this pre-processing, adding that one, then the parsing that message into the message blocks that ensure that that message and its padding is divided into equal blocks of your 512 bits. So then you need to set up the initial hash value first. Once the message is pre-processing, the initial hash value should be set up in this SHA. So how it will be set up? So this initial hash value, which is the 8, this initial hash value is the 832-bit of your word. That means you can multiply 8 into your 32-bit word. That will be taken as an input to fix the or initialize the hash value. So this 32-bit word that obtained by taking the first 32 bits of your the fractional part of your square roots of the first 8 prime numbers. So these initial values are randomly chosen in order to initialize the process and gives a level of your confidence that no backdoor exists in the algorithm. So once this initial hash value is also set up, you have the input message, which is fixed in size of your 12 bits, every block size. Then you by taking any prime numbers, the first 8 prime numbers, and you just use the 32-bit word and initializing the first hash value, because somewhere it must start. So the first hash value will be computed in this. So after that, the hash functions, this is all about the processing of your messages. So as said, After getting that, the partition the entire message into your n 32-bit blocks, that m to the power of 1, m to the power of 2. These are the number of blocks. So that depends on the number of bits in that entire message, that is depend. And after that, as said, every 32 block is further divided into 32 bits of blocks. The reason is to protect every word in that block so that the attackers cannot guess the entire message. So this is the initialization part. And after that, it goes to the second component of your hashes. First component is pre-processing of your message. Second component is computing the hash value or the hash computation. So in the hash computation, each message block is processed in a sequence, like the first message block of your m to the power of 0, then next message block m to the power of 1, and so up to m to the power of your n blocks. So every block is processed in a sequence. And it requires the 64 rounds to compute the full hash output. So each round uses slightly the different constant, because to make sure that there should be a collision resistance, so that for every block different constant will be used, so that when this block is processed, their output, their digest should not match with each other. There should not be any conflict. So first the message schedule is prepared, which block is execute first and which block is next. So that will be processed, and after that, then the 8 working variables will be initialized for these blocks, because when we divide this into the number of words in every block, it takes the 8 constants are required. Then intermediate hash value is calculated, and that intermediate hash value finally used as an input to the next round, and it will give the digest. So in this case, it starts with the fix the initial hash value as mentioned. For that, it takes the 832-bit of your word, and then start the h1, and then from the previous hash value, a new hash value will be calculated for the new block. So how it is calculated? The new hash value is calculated based on the previous hash value of your previous message plus the new hash value, previous hash value with the message, which is given as an input to your compression function, which takes the intermediate value of 256. So by adding these two, it will generate the new hash value. So where here this C is your SHA, the compressed function, as we said, where C is nothing but your SHA-256. So every time it takes the M0 block, then M1 block, your M2 block, and so up to your Mn block, and for every block it gives the one digest that finds the hash of your I, which depends upon the previous hash of these messages. So this message plus this compressed function gives the new hash value, and for computing the sequence of hashes, this hash is added to compute the hash of your the next function, that is I plus 1. This functionality goes on. So this means in this case, this means the compression function and the modulo of your 2, which is adding the previous hash and the new hash value along with the new message. So this hash function finally generates a final digest, and that digest is used for the exchanging the information in distributed network. So I'm not going in detail into the compression function. If you are interested, you just go through that and find out how this compression will be done by following the block cipher text method by following 64 rounds to calculate to give the new digest value of any block size. So here, if you see, as we can say, if in the abstract way, if we say that there will be a message which we can take it as your input message. This input message is divided into your blocks, like m to the power of 0 block, your m to the power of 1 block, and so up to m to the power of your n block. So this block is taken as an input, and there will be an initialization of your first hash function. That hash function is of your size 256 bits initialization vector, which takes the 832-bit word. So that hash function, initial hash function, will be given as an input to your compressor of your secure hash algorithm 256 compressor, as well as another input is your first block of your first message. So it do it the bitwise operator here, bitwise operation, and whatever the output comes, that the size of that output is 256 bit digest. That digest, we call that your h to the power of 1 digest. That will be given as an input to the compressor, and the compressor will takes another round of your next block, that is m to the power of 1, and it generates the 256 bit compressed size of the next digest, that we call the h to the power of 2. And this process continues. It takes the M2 last block in a sequence way, and the what you call the n minus 1 of your hash function value will be taken as an input by this compressor SHA-256, and gives the fixed message digest of the entire message as your 256 bit message digest will be given. So this is the general, the design case of your secure hash algorithm of your 256 or SH2 secure hash algorithm. Okay. So if you have, I would like to pause here. If you have any questions, please feel free to ask.
Yeah. The constant iterator that was discussed when we were talking about hashing, is that's calculated with the message itself, or is that standard for SHA?
Standard for SHA.
Okay, so no matter what message you send, there will always be the same kind of constant iterator.
Yeah.
Okay.
Right.
Thank you.
Any other questions? Okay. So if there is no question, then let me ask you that in the pre-processing of this secure hash algorithm 256, what are the main points that one should take here into the consideration? Yes, please.
The size of the message.
Correct.
Notably, if you bring it into 512 bit.
Okay. Because this is very important, the initialization of your secure hash algorithm. Because in your lab assignment, we are going to ask you to generate a key when we complete the public key infrastructure. We ask you to generate a key. You need to write the code on your own. Then once the key is generated, then we use the message authentication method. And then we use the message authentication method after generating key. Then we do the hashing. And using that hash value, you're going to generate the digital signature. And then you're going to verify the digital signature. So when you are trying to write a code for hash, it is very important. Because you need to mention what is the maximum length of your message that SHA can take. So what is the maximum length of message SHA can take? I forget your name. Yeah. 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 Okay. So what is the maximum message length that SHA can see? 256. It gives a pixel length of output that is 256. Input size. Input size, it may take one character or 2 to the power of 64 length of characters or message. Output is fixed, 256 values. Now, what is the next step? If the number of bits in a block of message is less than 512 bits, what kind of action should we take to normalize it? Another? Padding. So, to do that padding, what operation we use means how many bits we need to add that.
It's if message is L log 512, and then so it's LU1 bit as one, and then K amount of 0 bits, and that's
That's
L log.
that. So that is, we can do the modular operation to find out, how many bits that we need to append, we need to add. That is L plus 1. One bit we use for separating the original message bits and the padding bits. Okay. So once the block size is pre-processed, then what's the next step? The result process. Number of blocks are divided. Okay. So what is the next step that we do in hashing? Further, those blocks are divided into words. Further, those blocks are divided into words that is size of your 32 bits. So total, how many words will get in 512 bits means 15 words. So then those words will be processed by the 64 rounds of iteration from the language of each word. Then the blocks will be given to completion function, like m to the power of 0, 1, every block is given. Okay, when we have a message, we have done pre-processing from the message, we divided blocks. Yes, please.
I apologize. Just is it the words that are hashed together in this
Yeah.
message? And,
No. The blocks will be given.
okay, so words are processed beforehand, and then blocks will be
Given as a
yeah. Okay.
Yeah.
Thank you.
So now the next thing is what we are doing. We have message. We check the pre-processing the message that whether it is fixed length of 512 bits or not, and as Nagan said, if any number of bits are less, we do the padding. So now blocks are okay. So after that, we need to do the hashing for that. So the next step is the initial hash value should be computed. So from where we compute initial hash value means you take the first 8 prime numbers generally. From first 8 prime numbers, you try to compute a 256 bit digest hash value H0. So that initial hash value is not there in the message. Initial hash value will be computed out of the message. So how it is computed means by taking prime numbers, first 8 prime numbers. So those prime number size is 32 bits. Means every prime number represents 32 bits. So then we will get the 256-bit initialization vector. So now we have the message block, we have the initial hash function. Because for every compression function, it takes 2 inputs. One is message block, another one is previous hash function. So initially, there is no previous, so we need to initialize. How we are initializing means we are taking the 32-bit prime number. So from first 8 prime numbers, you can randomly select any one prime number from any one prime number and represent that in 32 bits, and that 32 bit is converted into 256 bit hash value. Correct? So once we have this and the first block, then every block of message will be processed sequentially. How it is processed means the output of first compression function and the input of your second block. That gives the next hash function. So the output of this compression function and the next block will be given as an input to generate the next function. So finally, for entire message, get only one digest with the 256 bit in size. Okay, and that digest is transferred or exchanged between the users in the open network. Open network. And another one is here, very important part is whatever the message is there, this message is pre-exchanged. We call the using secret sharing, these messages are pre-exchanged. So on receiver side, receiver also do the same hash function, SH4. Sorry, the SH2 is used. Same message will be there with the hash function. Means while you send a message to me, I will use the same message. I will divide the message into blocks. I will follow the SH2 only by this mechanism. I will find one digest. And whatever digest that you are sending, I'll try to compare that digest. You are sending digest and my computed digest. If it is matching, that means the message is not tempered. If it is not matching, message is tempered. So in the previous lecture, we have seen that if at least one character change, the digest is changing, right? So when you do the bitwise operation for received digest and your computed digest, if it is not matching, that means what? While that message is transferred, someone tempered that. Correct? The attackers did some fabrication or modification or something. Correct? Yeah.
Apologies. Just wondering if the initial vector is randomly chosen from prime numbers, how do you pick the same random number that I picked when I made the hash I sent it to you?
Yeah, that is what when before sending this hash value, there is one method in there you might have heard about secret sharing.
Okay.
Secret sharing.
Yeah.
So that secret sharing done by public key infrastructure.
Okay.
So that we will discuss in.
Okay. So it's as part of the message sent to you, inform them I used this prime number.
Yeah.
Okay.
Yeah.
Thank you.
So I hope it is clear, right? Yeah. Okay. So then further we can move. So this is the basic design part of your SHA-4 algorithm. And the next one is if you have the what you call the Kali Linux or any Linux operating system, in the dollar, you can use the command to check it out. The open what you call the SSL command, and then you can give any name for your text file, that raj.txt. You create a txt file, and that you can give any message. And if that text file is given as an input to this tool, open SSL tool, it will generate a digest as like A, B, 1, 2, B, C, like that, up to 256-bit fixture size digest. For your practice, you can do on Linux system. And after that, you open this file by using the command called your, if it is created with nanocad, you can open this raj.txt, and in that, whatever message is there, you try to change any one bit in that text file, in this text file, any one message in this text file, and then again you try to compute the that after changing that you try to do the open SSL file and give that input as raj.txt file, and then whatever digest that you will get here, digest like some B A dollar A B C something like that, again 256 bit of your digest you will get. Then you try to compare this digest and this digest, try to compare. If they are matching, when the comparison result is 0, that means the content in this text file and the content in this text file is not changed or modified. When you're comparing these two digests, if it is not equal to 0, means someone changed this text file. Someone changed this text file. So that is verification. First generation and then the verification. So this is all about the SHA-256 the algorithm. Okay, I hope it is clear for you, right? Okay. Is it fine? Okay. Shall we move further? Yeah. So then what are different patterns of this hashing of your data? Okay, different patterns. So there are, the independent hashing is one pattern, or repeated hashing is another pattern, combined hashing is another pattern, sequential hashing is another pattern, hierarchical hashing is another pattern. So there are 5 different patterns of doing hashing. So let us see this one by one. So why? Because these hashing of your data will be most useful in the blockchain technology, especially in the application of your Bitcoin. So in independent hashing, so whatever data that you are having in independent hashing, whatever data is there, suppose this is my text file, like raj.txt text file. In that text file, I'm having a content or message that hello message. So this message size, it is more or less than 2 to the power of 64 bits. But it should not exceed more than 2 to the power of 64 in it. Okay. So now this hello function is given as an input to the compressor function, that is your hash of your Raj text file. When you do the hash of the Raj text file, whatever the message is there in that message, it will be generated digest of size your 256 bit in size. Like if it is combination of that represents in the form of your hexadecimal. And another file is there. Suppose if I am sending another message to which is called the name, suppose your Raj 2.txt file, where the content is bold, the apostrophe, then it will give independently or separately to your hash function, that is your Raj2, and will generate a different digest. If you see this, it will give you a different digest message. This is one way of doing. Means if you have n number of messages, if n number of messages are in terms of blockchain or cryptocurrency, we say that if you have n number of transactions, every transaction can independently hash. Is one option, independent hashing. So every hash, whatever digest we will get, all those digests will be stored in a digest table or a hash table. So after that hash table can be exchanged. If you have n transactions, you do n hash. So n hash compression will give the n digest. All those n digest in sequentially arranged in a table, and that table will be distributed among the users. This is one way. So that independent hashing. Another one is to make more secure for these hash function. So I have the message, instead of creating 2 different files for 2 different messages and doing the independent hashing, Instead of that, I can concatenate this message with this message in a single file as your raj3.txt, that hello world, and do the hashing. So whatever digest that you are getting, that digest can also will go through another hash iteration. So that we call the repeated hashing. But the sender and receiver should agree that how many repeated hashing done on sender side and how many hashing done on receiver. Receiver should follow the same sequence. If sender do 2 hashing, receiver also do the 2 hashing. If sender do n number of hashing, the receiver also do the n number of hashing. So there should be a cooperation from sender and receiver is another part. And the third one is, I think, is it clear from these two? Independent hashing means the message is divided and do separate hashing. Repeated hashing means you club together, concatenate together and do the hashing. Third one is your combined hashing. The combined hashing, in repeated hashing, the hash function is repeated. In combined hashing, before do hashing, you do the concatenation of 2 different files, hello world, and then give as an input to a single hash that we call combined hashing. Combining the message first as an input to your hash function. In repeated hashing, they also concatenated before giving as an input to your hash function, but the number of hashes are repeated in repeated one. Yes, please.
So for repeating hash, if you set that to 1, it's the same as combined hash. If you only do 1.
No, for different applications, different approaches will be used in blockchain.
Yeah.
So repeated hashing is the most, the preferable hashing pattern in blockchain. Because as soon as new block is generated, it uses the previous hash to give the name of new block.
Yeah.
So for different applications, different hashing patterns are used. Yeah.
Different.
Yeah. Yeah.
Thank you.
Yeah. And then the sequential hashing, as we saw, the hello will be hashed and that hash will be combined with the new, the message with the hashing value. So this is what we have just observed in the previous case. In SH, the SHA-256, we followed the sequential hashing. Correct? Because the input message is hashed first. Whatever the hash value is there, that is concatenated with the new message, and these two are given as an input to the your compressor function. But initially, before start this process, initially one hash is computed. We call that h of 0. Then this is your h of 1. Then here it is h of 2. The sequential hash which we just observed in this case. So SHA algorithm, it follows the sequential hashing. Yeah. Okay. Right. So then another pattern is your hierarchical hashing. In hierarchical hashing, it repeats the independent hashing and repeated hashing. Independent hashing and repeated hashing patterns together become a hierarchical hashing. So, but here, to make your message more secure, you are combining different patterns together. So here see, this one is one independent hashing. This pattern is one independent hashing. Then this hash and this has the together generating another hash. So it is repeated hashing. These hash are generating another hash. Repeated hashing. So these are different types of your hashing. So please remember for your examination purpose also. Remember that what are the different pattern of hashing is there. So you can answer that. And there will be a multiple choice questions only, but you select that 2 hashing pattern, 3 hashing pattern, 4 or 5. So ultimately we classified as 5 patterns. So select as 5 patterns. Right? So what are those? Means one is independent, repeated, sequential, and the hierarchical. Okay, so these hashing patterns. Remember, so to easily remember, we have given this in pictorially part. Okay, so then comes to the importance of your hash pointers, because in blockchain technology, we have seen that first one block will be created. Suppose in block 1 is created, and based on the information of this block 1, the next block will be created, like block 2. Based on this block 2 information or message, your block 3 will be created, and so and so. So in this case, if you observe, if you relate this block technology with the data structures, because every block is consists of data, right? Data in terms of the sequence of information or collection of information. So that will be stored in one block. So it follows the data structure in your programming language. So in data structures, how one block is related to another block is addressed means using pointers. Because when the block will be created and what is the size of the block is unknown, unpredictable, right? Block in this case, block 1 size may be less than the size of your block 2, and block 2 size may be greater than the size of your block 3. Why? Because of the user's transactions may be updated. Okay, in that updated one, the sizes will be varying. Sorry, block 1 size is lesser than block 2, block 2 size is lesser than block 3. So as every block is created, as per blockchain technology, the created information will not be destroyed, but new information will be adding, right? So every time size increase. So if you go and store these values in a sequential memory, that will not suitable. So in that case, what you take, the dynamic memory will be taken. To address the dynamic memory in data structure, we follow the pointers, because one block is created at what location, and its sequence of memory location is not sufficient to accommodate block 2. It may go and find the suitable location in the memory where it is, and that the block will be created there. So but there is a relation from first block to the next block, so there should be a relation, that relation addressed by the pointers. So as we are saying that in hash blockchain technology, the hash value is used for addressing the every block identity. So every block should be identified in terms of the pointer. So if the H0 is given to this block of data and H1 is given as an identity for the next block, then this H1 is computed based on the information of your H1. So it requires a pointer for addressing. So it is in cryptographic hash pointer, it is often called as your hash references. It is a pointer to locate where the some information is stored, where in which block that information is stored, and the hash of that information is stored in the next one. Hash of this as we said, this hash value plus the data block of information value will be used to compute the next hash value. So this hash pointer points that this hash pointer value is based on this data. So it gives where this information is located, that gives the information. So with the hash pointer, we can retrieve the information. With this hash pointer, we can retrieve this information. Where that information is located, from there you can retrieve that. So what is the meaning? And check that the information has not been modified. So use the same information which is pointing by this hash and do the hash value, supply it as an input to your SHA-256 hash function and find the digest or the hash value, new hash value, you can say, and compare this new hash value, compare with the previous one, suppose h1. If both are matching, it will give 0. That means no modification. If not equal to 0, then there is a modification. So by computing the message digest and then matching the digest with the stored hash value, if it is okay, means by doing the bitwise operation, if it is giving same result, then no modification, or else it's modification. So what is the beauty of this one means, this we can represent that the new hash value will be computed based on the data, and the hash pointer pointing where the data is there. In the previous block it is there, location will be there. So in this case, if any attacker, or if in the blockchain technology, if any user changes any transaction, suppose initially, let us assume that here in this data part, transaction 0, transaction 1, transaction 2 is there, and based on these 3 transactions your hash is computed. If any user, suppose, update the transaction 3, then based on this transaction, this new hash value will be computed. New hash value will be computed. Okay. So then, why this is means, we'll discuss more in detail about how it will affect in the blockchain technology. That means because of the networks, pros and cons. If your network is slow, some users are computing the transaction in a faster rate. Some users are computing the transactions at a lower rate, but both are doing at the same time, but processing time is increased. So that Mark, right? Nathan. So Nathan computing 3 transactions, I am computing 4th transaction. Okay, but what happens? My processor is slow, his processor is fast, so his 3 transaction block is circulated among the network. My 4th transaction is getting delayed. When it is getting delayed, then what happens? My computed hash value will not be updated. When it is supposed to update means mine is okay. He has to update his value. That means by adding 4th transaction, you need to add the 4th transaction, you compute the new hash value, that new hash value will be updated by the next block, and next block, until all the hash values updated, new block may be created. So in this case, I am a genuine user of the network, and the Neti is, for example, don't mind that, is the malicious node in the network. So by that way, detecting tampering is easy. So that's the reason the hash pointers are used in the blockchain technology. Okay, so we'll see that. See, to detect the tamper detection by using this hash pointer means, see, initially one block is created, one hash is created, hello world, by a user R1. So this is by using this message, the R1 hash is created. So after that, what happened? This message is updated. Hello world. When this message is updated, it must compute the new hash value, new R value, R1. Correct? So if any changes happens in this message, then there will be a change in the hash pointer. So then if there is a change, so new hash will be updated. Based on this new hash, new block name will be changed. Or any existing blocks which are depending on this R1, they must be updated every time. Sequential, yeah. Correct? So easily it can be detected that whether this message is tempered or not. Right? So that is, making tampering a hash chain computationally is a challenging one. So how to identify that one means to identify based on nuns. Based on the nuns, the time, at what time these hash values are computed. If you see at 0 nuns, the text to be hashed for a hello world at 0 nun, it will give one output as a digest. Then at 1, it gives another the digest, because as if any nuns are changed, its hash value will be changed. So for every nonce, for every new transaction which is updated in the block, new digest will be calculated. So new digest will be calculated, that is restricted based on this nonce. So new hash value will be computed. So from this new hash value, what will be there? The data, updated data will be there, means new transactions will be there in this, and with the new nonce will be there. To compute this hash value, updated transactions are there. Let us assume that the first transactions are transaction 0, transaction 1, transaction 2 is there in the data field. And that will be this data, and the none 0 is given as an input to your hash 2. So one hash is created, like hash 1 suppose. If another transaction is added, T3, at the none of 1, so new hash will be created too. For another none, suppose a 2, new hash value. So based on nuns, every user in the network, they first to try to go and check these nuns, which are the previous nuns or updated nuns, to easily identify whether new block or it is the old block which is repeatedly exchanging within the network. So that by that way it can make the tampering one. So in detecting the tampering from the hash pointers, as said, it is a hash chain one. So what happens? To compute the, let us assume that this is block 0, your block 1 and block 2. So from your previous block, this previous hash is computed based on previous data, previous block data. So data means message. That message given as an input to your compressor. So it gives the hash value, and that hash is concatenated with new message, as we saw in our the hash SH-256. We have seen, right? Initial hash value given as an input to your compressor with the new message as an given. So previous hash and your new message, let us assume to recall that like M0 or M1 and your hash of your H0 will be given to your compressor. So it generates a new hash. That new hash compressed with the message 2. So what happens in every case, it is saying that this hash is pointing based on which message this hash is computed. That means previous block message. So that is location. This pointer is giving the location of your previous data. That means if anything change in this data field, it is going to be changed. When it is changed, it has to update. This data will also be changed. This hash will also be changed. If another block is there, that hash value also be changed. Means what it says, if any block is updated, all the sequence of blocks must be updated. That means in a distributed network, as we discussed in the blockchain, if any one user updates information in one block, that must be triggered in every other block. If you recall the concept of your petroleum industries, correct? If any one user updates information, that public bulletin should be available to all others. So in this case, if any user updates in the block, their hash value will be changed. When that hash value change, every other block's hash value will also be changed. Okay, so that is the advantage of your hash pointers to detect any tampering. Means anyone is doing some wrong transactions or not by using the previous information, right? So for that, it follows the Merkle tree organization of your hash pointers. So in Merkle tree, it is a binary tree. In this binary tree, what happens? Let me use this concept for this. In binary tree, suppose if I have a message that capital A, capital B, capital C, capital D, suppose this message is individually hashed. Capital A will be hashed. We call this as leaf nodes. So if you recall the property of your tree says that tree will have one root node, intermediate nodes, and leaf nodes, right? So the nodes which are not having any parents, they are leaf nodes. Those who are having the parents, and if they are not a designated node as root, they are intermediate nodes, and one node is your root node. So this Merkle tree, these hash pointers organized based on the Merkle tree concept. What is Merkle tree concept means? It is a binary tree. Binary tree. Binary tree means every node is having exactly two leaf nodes. Exactly two leaf nodes. So in hash pointers, how we do, every individual character in the message is hashed, hash of A, your hash of your B, your hash of your C, hash of your D. Okay, they will be hashed. And after that, these two give the another hash of your A and B. So which concept it is giving now? If you call the hash patterns, first one is independent hashing, right? Correct? Then in the second case, two hashes are combined. Two hash values are combined. So which pattern it gives? Is it the repeated hash or sequential hash or the what you call the distributed hash or hierarchical hash?
Repeated, combined, sequential,
Hierarchical hashing. Okay, so Merkle tree follows independent hashing, then the hierarchical hashing. So then HAB is computed, then these two hashes are come together to become a parent, that is hash of your C and D. Then these are make as your hash of your A, B, C, and D. So at leaf node in Merkle tree, they follows independent hashing. All even the remaining intermediate nodes and your root node, it follows the hierarchical hash pattern. So this gives, that means if any changes happen in any of these hash, that must be updated in the Merkle root. So that means if any of the users in the network from A, B, C, D, any of the users become a what you call the malicious node or the attacker, if they want to change the message here, their hash must be updated here, then it must be updated here, then it must be updated in the root level. So until they reach to root level, maybe the new block will be created. So for new block, new Merkle tree will be there. So attacker cannot be attacked. Yes.
So the Merkle tree is about the distribution of your hash message out to the network, saying each endpoint, each leaf is one of our users in our network.
Yeah.
And because of how we hash together in this hierarchical way, no one user can change it.
Correct.
Okay.
Yeah. Because because it is a distributed one and
Yeah.
open network, right?
Yeah.
Initially both are there in the network. So I'm having my hash value, you are having your hash value. Then our both hash value will be combined. So if you change anything, that will reflect in our both combined hash value. If I change anything, that will affect. After a period of time, Lisa also joined. Lisa, right? Marina also joined. So she will also do hashing. And if another person, Ravina, right? Ravina do. So their hash value, our hash value together.
Yeah.
Okay? So if among us, if anyone become malicious node, if I do anything change, then our both combined hash value will be changed.
Yeah.
If that hash change, you can easily detect that is not the hash value which you are already having. That means I did something. So if any tampering done, that means anyone in the network can do it. Yeah. So so this is the hashing, the Merkle tree hashing process. So in this case, as we see, at leaf nodes, if any transactions changed, so the hash of T1 will be done. It will generate one hash value. That hash value for another transaction, another hash is there. These two hashes are given to your hash function to generate another hash value. So like that, it combines all the hash values that will reach to your Merkle tree root. If any transaction changes at the leaf node, based on that, these hash values will also be updated until root to update in all the blocks. So this is the organization of your hash pointers in a tree. Okay. So this, if you that entire concept take into your blockchain as a hash chain, in every block, to generate a hash value, there will be nonce that gives at what time this hash value is generated, and based on that nonce and the previous hash value, it generates the new block or this block current block hash value. And this current block hash value will be comes from your Merkle tree. If any change happens in this block hash value, that will reflect in the Merkle tree. Okay. So if the next block B1 is created, that is based on previous hash will be taken as an input, and the data which is there in this block is taken as an input with new none, and new block hash will be generated. So like that, from B0 block to B1 will be generated, B1 to your B2 will be generated, and so it leads to your Bn blocks. That means if any change happens in the B0 block, that must be updated in all subsequent blocks. So this is the blockchain as a hash function. So if anyone asks you that what are the different components in the blockchain as a hash chain, means there will be 4 components. 1, previous hash. 2nd, none. 3rd, the new hash value, and 4th one is Merkle root. Okay, so this is all about the cryptographic primitive of the first part, which is useful for your blockchain technology. In the next class, we'll try to discuss this is hash is keyless, right? In the next class, we discuss about public key infrastructure, where the symmetric and asymmetric keys are used to do the digital signature. Okay. Thank you. If you have questions, feel free to ask me, or else we'll discuss. Thank you so much.
Thank you.
Thank you. Have a nice day. Yeah.